Swayam Prabha. Digital India. Educated India.
Welcome back to the lecture series in bioelectrochemistry. So, today we are into the 10th lecture or the last lecture of the second week, the 5th lecture of the second week. So, as of now we have talked about the standard potentials, and today we will be concluding this week with the Nernst equation. As I told you that we are running slightly off because we are supposed to do the different kind of electrodes and potentiometry, but I purposefully devoted this week on the basic fundamentals, and today is today's class is kind of this is one of the most important and critical aspects what we are going to deal, that is Nernst equation. Nernst equation as its genesis, it was formulated by Walter Nernst back in the last decade of 18th century, around 1890. Yes, series of papers which talked about, he worked on several areas, but one of the areas what we will be talking today is about EMF, electromotive force. So, as of now, just even before I give you the basic concept and the write up of the Nernst equation, let us recollect. During our standard 8th or 9th or 10th, we read about Le Chatelier's principles. Those who have forgotten, just recollect. Say for example, there is a reaction taking place, say A plus B is equal to C plus D, okay, or A plus B reversible, like will make two products C plus D. So, now we always remember that if the concentration of A plus B is higher than the product or the reactant, if the reactant which is on the left hand side A plus B giving rise to C plus D. So, if A plus B concentration of A plus B is higher, then automatically the reaction will proceed towards right direction or towards making more product. But say for example, it is a reversible reaction, if C plus D or the product concentration is higher, then the reaction will move on the reverse direction, it will make A and B, of course within the framework of thermodynamics, if it is being allowed and what sort of energy it will be needing. But this is what we have learned, and based on that Le Chatelier's principle, we had the activity coefficients and we have developed K is equal to, if you remember, absolute C multiplied by D divided by A multiplied by B, and all these things you all have studied at some point or other. So, the key question what Nernst equation or Nernst himself tried to answer in terms of the EMF and as well as taking the analogy of Le Chatelier's principle is, what will be the driving force? Could we calculate the driving force on a reaction like this, A plus B, the reversible arrows to C plus D? What is the total driving force? In other words, having said this, let me give you a philosophical situation, or much more I would say a practical situation, and then the philosophical, scientific philosophical thinking behind it. So, say for example, we have talked about the silver and cadmium electrode, you remember, and we remember that in the cadmium we are having the oxidation and in the silver we are having the reduction, right. So, the electrons were leaving the cadmium electrode in the outer circuit and they were being drawn by the silver electrode on the right hand side, right. On the left hand side we had cadmium, on the right hand side we have the silver. If you recollect, if I just go back of where we have drawn that kind of electrodes. So, here you see the cadmium electrode, here you see the silver electrode, and the electron is traveling like this. Now, say for example, in this situation where we actually calculate the standard potentials of cadmium as well as silver, what will be the driving force? Could we calculate the total driving force in this situation? That is because if you remember, we never given any value of the E here. Okay. So, what is the driving force which will drive the electrons, which will make it to do the work from moving from cadmium to the silver electrode, solid silver electrode. Okay. So, this is what Nernst equation has addressed, and that is what we are going to talk about today. So, let us resume the lecture. So, this is our lecture 10, week 2, lecture 5 of week 2, W2 L5. Okay. And the topic what we are dealing today is Nernst equation. So, as I told you, the Le Chatelier's principle tells us that increasing the reactant concentration drives the reaction to the right, and increasing the product concentration drives the reaction to the left. Okay. This is what Le Chatelier's principle tells us. So, in other word, if we write a reaction like this plus and E, make it B B. Now, if the concentration, so this is on the left hand side LHS and this is on the right hand side RHS. So, now if the concentration on this side is more, so the reaction will proceed. If the concentration is more, the reaction will proceed towards right. Similarly, let us use another color. If the concentration here is more, then the reaction will proceed towards the left. And what Nernst equation tries, the net driving force for a reaction is expressed by Nernst equation. The net driving force for a reaction is expressed by Nernst equation. Okay. And whose two terms include. So, if I put the Nernst equation in place, so it has basically two terms. So, the Nernst equation for the reaction what just now I showed, say for example, if this is the reaction and if I had to put the Nernst equation in place, so it will be E, which is in volt, standard potential E0 minus gas constant, absolute temperature, number of electron, Faraday's constant, natural log, this is the natural log, and concentration of B, this is concentration of A. So, essentially what I am talking about is reactant, so the product A and okay. And this is your number of electrons, what is being shown here. Now, if you look at this equation, there are two terms. One is the standard potential and there is another term. This is your standard potential term and this is the second term, which is what are these two terms signifying? The net driving force for a reaction, as we have said, is governed by the Nernst equation, and whose two terms include driving force under standard conditions. So, this is essentially the driving force under standard condition. This is one, the first term, which is where basically E 0, which applies when all activities are unity. We have already talked about it, when all activities are unity, or in other one. And the second one, the second term, which is this term, pull it out. This second term is showing the dependence on reagent concentration. And if you see the second term, reagent concentration. Now, what does that physically means? There is a physical meaning to this two things, and for that I will be again going back, taking help of the diagram here to make you understand. So, say for example, when we were talking about the standard potential out here, whether it was cadmium, whether it is silver, when we were measuring the standard potential, we assume everything is unity, okay, all concentration, everything is unity, and we calculate the standard potential, which is not an issue. But the problem is, in real life there may be situation where it is not essential that everything will be unity. I may vary the concentration on, say, silver side, I may vary the concentration on the cadmium side. For one unit I know this is it, with that I have to add for that many unit how much it will be, okay, something like that analogy. So, if they are not unity, if the concentration, if this value what we talk about, now coming back having shown you this, if out here, if these values are not unity, if this is not unity, or if this is not unity, then the second term what you see, which is coming here, will come into play. Now, if you look at this term, what does this term stands? And actually, so this is in volts, okay, this is in volts. Now, what about this term? How this term is in volt or anything, okay. So, we will talk about it now. Now, remember this term, now we are going to do a unit analysis of this particular term. This particular term, if I look at it, RTNF natural log, this term could be further dealt. Now, before I get into this term, let us put the values, okay, of, let us put what stands for what. Your E 0 is standard reduction potential, since we are only dealing with reduction potential, standard reduction potential, where A B is equal to 1, which is the unity, I mentioned that, okay. Then you have R, which is the gas constant. This gas constant term is 8.314 joules per Kelvin mole, okay, and which could also be written if it is in joules. So, if you remember, in the very first class I told you joules is the expression for work, and work is Q charge into the potential. So, potential could be expressed in V and charge could be expressed as Coulomb as C, right. So, I can actually write this as a unit analysis, and you will realize where this will come pretty handy. C into V per, this is degree, this is temperature, okay, Kelvin. So, I actually can write 8.314 CV, unit of temperature per mole, okay. And this will help us in doing the analysis of the unit analysis, okay. Then T is temperature in Kelvin, temperature in Kelvin, and then we have N, which is equal to number of electrons in half reactions, number of electrons in the half reaction. So, remember, whenever we are doing Nernst equation, we have to ensure that we do the comparison with same number of electrons, okay. Then F is equal to Faraday's constant, which is 9.649 into 10 to the power 4 coulombs per mole, and then you have the activity of the species, activity of the species in question, which is the ith species, okay. It could be anything A, B, whatsoever, okay. So, now what you can do, the logarithmic term in the Nernst equation is the reaction quotient, which is your Q, which is in this case it is B upon A by A, okay. Q has the same form as the equilibrium constant, but the activities need not have their equilibrium values. This is an important part to realize, okay. So, the activities need not have their equilibrium values, and pure solid, pure liquids and solvents are omitted from Q because their activities are unity or close to unity, okay. So, remember, for the Q you cannot use pure solid, okay, you have to omit it. Pure liquids, again you have to omit it, and solvents you have to omit it because their activity are unity, and if the activity becomes unity, then this whole equation will become 0, okay. Now, or close to unity. Concentrations of solutes are expressed as, this is the important part, concentration of solutes are expressed as, concentration of the solutes are expressed as moles per liter this is one part, okay, and concentration of gases are expressed as pressure in bars. Concentration of gases are expressed as pressure in bars. Okay, so keep this in mind, and when all activities are unity, Q is equal to 1, if Q is equal to 1 as I was telling you, and then natural log of Q is equal to 0, and that will give you E is equal to E 0. So, now if you look at this equation, if out here, so this is the term we are talking about, if this whole thing becomes unity, then the natural log ln of if I denote this by q, that becomes 0, and in that situation your E is equal to E 0, because this whole term will become then 0. So, keep that in mind. So, now another important conversion what is being done is changing this natural log into the base 10, which is much more easy to work with. So, now the next thing is converting the natural logarithm into the base 10 logarithm and inserting the value of t. So, this equation works at the value of t of 25 degree centigrade, which is essentially 273 degree Kelvin, 273.15 Kelvin plus 25. So, that makes it 298.15 Kelvin. Okay. So, now Nernst equation at 25 degree centigrade is E is equal to E 0, now last term I am dealing with, minus 0.059, you are multiplying everything, 05916 volt divided by n log of by the potential change by 59.16 per. So, this is the electron millivolt for each factor of 10 change in Q, and this is that Q term for every unit change or for each factor of 10 change in Q. This is the amount which is changing out here. Now, what is important here is to realize how this V is being reached. So, this V could be reached in a very simple way. So, if you look at the original formulae, the original formulae was like this: E is equal to E 0 minus R T N F natural log A B V minus A, which is your Q. Now, what you can do is you can, so this one you can express as I showed you, V c per mole, and Q, one second. So, this is the unit of the R, then you have the K, which is coming from temperature, and underneath you have N, which is, it has no unit, it is just coming as it is just a number, and then you have Faraday's constant, and the unit of Faraday's constant is your coulombs per mole C upon mole. So, this is what you are essentially getting. So, if you now place it, it becomes, unit analysis becomes V c upon mole. Of course, you have the K here, you have another K here. So, this K cancels. So, you have V c upon mole multiplied by mole upon C, which is this one, C cancel, mole cancel, you are left with V. So, what you have V upon N, and this is precisely what you see here, V, which is in voltage, and N, it is just a number. So, this is in voltage, this is in voltage, this is the third voltage. So, you are dealing with 3 different voltages out here, and remember it, multiplying a half reaction does not change the E 0. You can multiply a half reaction by any way, and Nernst equation for a complete reaction is something like this. If you have to see the Nernst equation for a complete reaction, it is E is equal to E plus minus E minus, where E plus is the potential of the electrode attached to the positive terminal, okay, potential of the electrode attached to the positive terminal, and potential of the electrode attached to the negative terminal of the potentiometer, negative terminal of the potentiometer. So, that way if you look at it, this is the potential what you have on the cadmium in our case when we talked about, and this will be the potential what will be observed in the case of silver, because this is attached to the positive terminal of the potentiometer. Okay. So, keep that in mind. So, essentially once you add these things, you will be able to get the final value of the Nernst equation. So, what I will do, I will close in here, and in the next class we will be starting with the different kind of electrodes, and I will take a small example from here, how really to put the Nernst equation in place. I will devote some 10 minutes where I will give you a little bit more clues on it, and we will talk much more about next 2-3 classes about electrode and the potentiometry with this background. So, what I will request you, now we are almost halfway through the course, please go through the basics. These are the very, very fundamental basics what needed to be imbibed into your understanding, so that you can really develop a very good conceptual framework to understand the basics of bioelectrochemistry. Thank you.